Hello everyone, my name is Olga and I'm a sophomore studying electrical engineering.
Hello, I'm Thomas McMahon. I'm a sophomore and I'm studying mechanical engineering.
Hi everybody, my name is Andrej and I'm a junior mechanical engineer.
So this project focused on a historically important engineering problem, predicting where a spacecraft will land after re-entry. Specifically, we modeled the trajectory of the Friendship 7 capsule using mathematical tools from dynamics, calculus, and also numerical methods. So this project is based on a Mercury-Atlas 6 mission, which is one of the most important milestones in early space exploration. During this mission, astronaut John Glenn became the first American to successfully orbit the Earth in 1962. At that time, the United States and Soviet Union were in the middle of the space race, a period of time where it was an intense competition to achieve technological dominance in space. The success of this mission was not only a scientific achievement, but also a major political and cultural moment. However, one of the biggest challenges that they had was not going into the orbit, but coming back safely. That critical point was called the go-no-go point, which you can see here. It was also our starting point of the mathematical model. And it's a moment when the retrograde rockets are fired to slow down the capsule movement. Before this moment, the capsule is in the continuous orbit, and since the space is a vacuum space, there's no air resistance to slow it down, so they needed to fire the retrograde rockets in the opposite direction of the movement of the capsule, so it would come into the re-entry process and leave the orbit. Engineers needed to determine the exact moment when the spacecraft should fire its retrograde rockets to slow it down. If this was done too early, the capsule could land far off the target, but if it was done too late, it might have skipped off the atmosphere or missed the Earth completely. A key figure behind solving this problem was a woman called Katherine Johnson. She was a mathematician at NASA whose work was essential to solving this mission at a time when computers were still limited and not fully trusted. Katherine Johnson manually calculated trajectories, re-entry paths, and also backup landing coordinates. In fact, right before John Glenn's flight, he specifically requested that she checks the computer's calculations, and he said that if she agreed that the numbers were correct, he would be ready to fly. Now, I'll talk about one of the most important decisions in our mathematical model, which were the choice of the coordinate system. Instead of using the Cartesian coordinate system, we used the spherical one. The reason for this is that the capsule is moving around the Earth and not along the straight lines. Its motion follows the curvature of the Earth, therefore, it's much more natural to use the spherical coordinate system, which is centered at the Earth. So to describe the position of the capsule, as you can see here, for example, we use three variables, which are r, theta, and phi. R represents the distance from the Earth's center, as you can see here. Theta is the longitude, and it represents east or west motion, and it's the angle that the position's shadow makes with the x-axis. And then phi, which is a polar angle, it represents the co-latitude. It's the angle that the position makes with the z-axis. And the more south we put the position of the capsule, the angle increases, and the more it goes north, the angle decreases.
To model the Friendship 7, to model the trajectory of the Friendship 7 capsule, we started with Newton's second law, F equals ma. Now, as Olga mentioned previously, it made much more sense to use spherical coordinates instead of Cartesian coordinates, since the capsule is orbiting around the spherical Earth. When we applied Newton's second law to all three of the spherical directions, we got three coupled differential equations, one for r, one for theta, and one for phi. Now, the radial equation tells us how the capsule's distance from Earth changes over time. Gravity pulls inward, that is this part of the equation, and the orbital motion creates an outward effect. This is that part of the equation. The longitude equation governs east-west motion, and the polar equation governs north-to-south motion. The thing about these three equations is, as I said previously, they are coupled, which means one cannot be solved without the two others. One thing we also had to remember and talk about, we have to consider, was the Earth's rotation. Since the Earth doesn't stop rotating during roughly 30 minutes of re-entry, if we ignore this, our landing longitude would be completely wrong. So we simply corrected this by subtracting Earth's longitude.
Now, to find our numerical solution, we used Euler's method as a way to go step by step through the re-entry process. The two important things we need for Euler's method is our starting point and our governing equations. And our governing equations give us the rate of change of the capsule at each time position. And so we use the time position of the previous step, which is x sub n and v sub n plus 1. That's the previous position, to predict our next position, x sub n plus 1. We do this for many steps continuously until our desired value is reached. And so our desired value for us was when the radius of the capsule, the distance from the capsule to the Earth, is equal to 0. And so that's how we know the capsule touches the Earth's surface. A really important consideration for us was our dt, or our time step. And this was so important for us because if our dt is too large, our model is going to stray away from the actual path of the capsule. But then if it's too small, it's a lot of calculation and it takes a lot of computing power, which we didn't have access to. And so we settled on a dt of 0.1, which got us the perfect balance of accuracy and the speed of our simulation. And so with our dt of 0.1, we didn't solve our equations like Katherine Donson did by hand. We actually created a code which would run the simulations for us. And so using our code, we ran hundreds of simulations to find suitable alpha, beta, and gamma values, which brought us to the landing point correctly.
Now, to actually run the simulation, we needed to define the initial state of the capsule's position at the go-no-go point when, as Olga said, when the retrograde rockets fire and the re-entry begins. We knew the geographic coordinates of the go-no-go point from the movie, and we knew that altitude was somewhere between 160 kilometers and 260 kilometers between perigee and apogee. But the exact altitude, the retrograde deceleration, and the direction of motion were not given to us. Therefore, we introduced three free parameters that are going to represent these values. Our alpha is our initial altitude, and our best fit value was 257,750 meters, sitting comfortably between perigee and apogee. Beta is the retrograde deceleration factor, the ratio of the capsule speed after the burn to its original orbital speed. Our best fit value was 0.982, which means that the capsule's orbital speed after the burn was at 98.2% of its original orbital speed. Now, I know that 1.8% sounds pretty small, but it's actually exactly what tips the trajectory from a stable orbit to the re-entry path. Gamma is our initial direction parameter. Our best fit value was 2.335, which corresponds to approximately 24.0 degrees north of east. What is important to say is that these values were not given to us, and we didn't look them up. We found them by running hundreds of simulations, adjusting systematically alpha, beta, and gamma by trial and error until the landing coordinates match the GLAN's actual landing coordinates at as close as possible. Our predicted landing coordinates were 21.313 degrees north and 68.550 degrees west.
As you can see, compared to the actual landing coordinates, our results are remarkably good. Our predicted landing is within about 0.1 of the actual splashdown location. And one thing to note is that small changes in our initial conditions can lead to very different orbits, and so precision in our alpha, beta, and gamma values was very critical. For our model, we used pretty much the simplest model that we could, which only used Newton's gravity and Euler's method, and this allowed us to pretty well simulate the trajectory of the capsule, and our results validate Katherine Johnson's calculations in 1962. And it must be noted that all her calculations were done by hand. Ours was done with computers, so it kind of even shows how more impressive Katherine Johnson's work is. For future improvements, we could consider drag during reentry. As the capsule comes into Earth's atmosphere, the density of air becomes a lot greater as we reach Earth's surface. And so to account for this would also improve the accuracy of our model. And another thing that we could have accounted for, but we did not, was the mass of the capsule changing during reentry. When the retrograde rockets fire, it uses up fuel in the capsule, and so that's going to decrease the mass of the capsule, and that's going to change the trajectory as well, but we did not account for that in our model here. And finally, with more computing power, we would be able to get closer results as well. We were limited to our laptops, and so we used as tight as tolerances we could, but with greater computing power, we can tighten down our tolerances for alpha, beta, and gamma and find a closer result. That's all.